Hi everyone, in this video we are tackling the concepts of continuity and differentiability. And continuity is actually one of the first things we talked about in this course, but we're coming back to it here to talk about it in a little bit more detail. And one of the things we said earlier in the course was if we were just okay speaking informally about this, a function is continuous if you can draw it without picking up your pen. And if you have to, pick up your pen as you're drawing your function, that point where you lift your pen is called a discontinuity. And so if I have an xy plane here, and I'm trying to draw some curve that represents y as a function of x, this whole point where I've been able to keep my pen on the paper, that's a continuous part of the function. But then if I have some kind of discontinuity like this, notice I have to pick up my pen in order to keep drawing this function after this jump discontinuity here. So again, hopefully you remember sort of intuitively what it means for a function to be continuous. Now to talk about continuity more formally, we define continuity at a point like this. A function is continuous at the point x equals c if the function f of c is defined, so the function f is defined at the point x equals c. And what I mean by defined is this. So as an example of something that is defined, if I take the function x squared and I plug in the point x is equal to 2, well then f of 2 is just 2 squared, which is 4. So the function is well defined at the point x is equal to 2. On the other hand, if you want an example of a function that's not defined at a point, let's take the function g of x equals 1 over x. At the point x equals 0, g of 0 is 1 over 0, which is not defined there. So that's one of the requirements for a function to be continuous at a point, is that it actually has to exist at that point. My second bullet point, so my second requirement, is that the two-sided limit as x is approaching that point c exists for my function f. And then my last requirement is that two-sided limit has to be equal to the function evaluated at the point c. Now if f is not continuous at x equals c, then we say that f has a discontinuity at that point. Next little bit of concepts here. This really is only useful whenever we talk about the endpoints of a closed interval. But what we're talking about is continuity from the left and from the right. And these definitions, I invite you to look at them closely and read them closely here. But from the left just means that you're talking about the same definition of continuity as it applies to left-sided limits. So notice where I have x approaches c, and then I have that minus sign that's telling me take the left-sided limit. And so I actually don't care about the two-sided limit anymore. If I'm only talking about continuity from the left, I care about the left-sided limit. And likewise, if I care about continuity from the right, then I care about the limit as x approaches c from the right side. So this one-sided continuity, if you will, is actually a little bit easier to attain than two-sided continuity. Right? So the requirements are a little bit relaxed. And so this is why we care about this as it applies to endpoints along a closed interval. So here we have continuity on open and closed intervals. So a function f is continuous on the open interval between a and b if f is continuous at every x value inside that interval between a and b. And likewise, a function f is continuous on the closed interval from a and b, between a and b, if f is continuous on the open interval between a and b, and f is continuous from the right at the lower bound a, and f is continuous from the left at the upper bound b. So just as an example of a one that I'm thinking of, something going on right now in my head, is that if you had, this xy plane, you might design or define the unit circle right here. So this green circle is supposed to be a circle with radius 1 and the center at the origin. So the center of the circle is supposed to be at the origin. It turns out that the formula that we could write for this circle is this. If I write x squared plus y squared equal 1, that is the formula for this green circle that I've just drawn. Now we might solve this explicitly for y, like this. I write y equals square root of then 1 minus x squared. And you may notice, whenever I write this in explicit form, it makes it a function of, makes y a function of x. So you give me some input value x, and then I'll calculate an output value y. And one of the things that makes functions functions is that there's only one output value for a given input value. And by convention, whenever we take square roots of things, unless you otherwise specify, we give you the positive square root, right? So we don't usually talk about the negative. And so in this version, in the explicit version, the function is going to look like this over here in teal, where I actually just have the upper semicircle, right? And the domain of this function, the place where this function is variable in the x-axis or in the input, that's what we call the domain. Well, the domain of the function is actually the closed interval between -1 and +1. So if I let x be any value between -1 and +1, we actually do get y values. And so we can ask the question, is this function in teal here, is it continuous at every point between -1 and +1? And yeah, it looks like I could draw that without picking up my pen. Of course, you can draw a semicircle without picking up your pen. And then is it continuous on the left at this point x equals a, right here, my lower bound? And then is it continuous from the right at the point x equals b? And the truth is that yes, it is continuous from the right at the point x equals a and continuous from the left at the point x equals b, because if you evaluate the function at f equals -1 and you evaluate the right-sided limit at the point x equals -1, those are the same value. And then likewise on the right side, or the upper bound of my domain, if I evaluate f of +1, I get the same value as taking the left-sided limit as x approaches +1. So we would say that this function here is continuous on this closed interval from -1 to +1. Excellent. This is a little section about differentiability. So when you can take the derivative of a function, we say the function is differentiable. And likewise, if you cannot take the derivative of a function, we say the function is not differentiable. And just by the way, when I say u, I mean the u in general, right? So just because if you don't remember the derivative, that doesn't make the function not differentiable. But it turns out that there are some points, and in fact some entire functions, where you cannot take the derivative. And so one maybe obvious point is that if a function is undefined at a point, then the function is, of course, not differentiable. So if I let the point x equals 0 be my point, and I plug that into that function there, of course, we say this function f is not differentiable at the point x equals 0, right? Because it's not even defined there. The next little bit, I'm a little bit informal with my language here, but if a function appears to be pointy at some point, then the function is also not differentiable at that point. And so what I mean is if I graph this function absolute value x, I'm going to draw you a miniature xy plane, and if we graph the function y is equal to absolute value x, this is what it looks like. It looks like straight lines on either side of the origin, but actually comes to a pointy point there at the origin. And so we say this function is not going to be differentiable at the origin. In fact, let me give a better illustration of the same idea. So to begin my little illustration here, I want you to just remind you of what the derivative means. So the derivative is where you have a line that's tangent to your function. So in red, I have the function x cubed minus x. And the blue line is a tangent line to that curve. And when we talk about the derivative, we're talking about the slope of the tangent line. And so if you can draw a tangent line to a curve, like we have here, that basically means that you have a derivative, because of course being able to draw the tangent line means that you, of course, know the slope of that tangent line. So you know, the fact that this tangent line exists everywhere for this red curve means that that red curve is differentiable everywhere. It means you can take the derivative. If you couldn't take the derivative, we wouldn't know what the slope of the tangent line is, right? So again, reminder about tangent lines and derivatives. Now let me show you this example. And in red, I have the function y equals absolute value x, which we were just discussing in the notes. And so in blue, I've put a line, and it passes through the origin, just like the red function does. And yet what I want to point out is that there's actually a lot of blue lines that pass through the origin and kind of only intersect the function at that one point, right? So you can think of this tangent line as being kind of on a like a seesaw, an upside down seesaw in this case. But there's not one particular slope of this tangent, of this line, that would make it a tangent line to our function. And so since I can't nail down a slope that sort of matches the steepness of the curve at that point, like I can, for this nice differentiable curve, that's why we say whenever we find pointy functions like this one, it's not differentiable at the pointy point. Okay, and then if a function has a vertical tangent line at a point, then we say the function is, again, not differentiable at that point. So let's consider this function, which is cube root of x, and think about what happens to this function when x is equal to 0. While x is equal to 0, the value of the function is well defined. So the value of this function would be cube root of 0, which is just 0. But now let's take the derivative. So whenever I say that h of x is equal to cube root of x, I could rewrite that cube root as the exponent 1/3. So I could say h of x is equal to x to the 1/3 power. So then, whenever I use derivative power rule, this shows me we're talking about 1/3 x to the power negative 2/3. And the negative in that exponent means I put it in the denominator. So I can rewrite this derivative as 1/3 x to the power 2/3. Okay, so where you run into an issue here then is if I try to take the derivative at the point x equals 0, it's supposed to be an x, at the point x equals 0, we're talking about 1/3 times 0 to the power 2/3, and 0 to the power 2/3 is 0, 3 times 0 is 0, and so again, this derivative is going to be undefined there. So that's why we say it's not differentiable. It's because it makes the derivative undefined. But I want to go back to this because in the sentence right here above, I mentioned a geometric interpretation. I said if a function has a vertical tangent line at a point, then the function is not differentiable at that point. So let me give you an illustration of that vertical tangent line for this particular cube root function. So in red, I have the cube root function. And in blue, I have the tangent line to the cube root function. And so notice that these tangent lines do exist when I choose a value for x that's not equal to 0. So most places, this red function is differentiable, so I can put a tangent line down. But you might notice that whenever I pass through the point x equals 0, that tangent line would be the vertical line. And I don't think that does, nope. So the way I have this set up to calculate my tangent line, it would require an infinite derivative, so Desmos is not showing it. But basically this tangent line should look like this vertical line whenever I talk about the tangent line at x equals 0. Right, and you can sort of look at the steepness of this red curve and see that it pretty much goes vertical. Or it does go vertical right at the origin. Okay. So that's what we mean by the geometric interpretation of that vertical tangent line. And that's why it's not differentiable. One last thing I'll say before the video is over. If a function is differentiable at a certain point, then the function is also continuous at that point. So differentiability implies continuity. However, it doesn't go the other way. It's possible to have a continuous function that is not differentiable. Just like this red curve is a continuous function everywhere, but it's not differentiable at x equals 0. And just like this absolute value x function is the same way, right? It's continuous everywhere, but it just wasn't differentiable at the origin.